Okay, welcome to the week 10 live session of the GPU Architectures and Programming course. So let's get started with today's content. Again, this will be a 2-hour session and we'll take a 5-minute break around 8 pm and we'll try to solve problems similar to your assignment question so that they become easier and more familiar to you guys. And post the session, you will get access to the slides and the recording. Yeah, I will skip this. So, so broadly what we'll do is go through a quick recap of what was covered in week 10, and after that we'll look at all the discussion forum questions and the TA's answers in the past week, and after that we will go to some questions from week 10's content, and with that we will wrap up. Right. So first of all, what was covered in week 10? So starting from week 9, I think we were talking about OpenCL. We spoke about the runtime model and things like that in week 9. In week 10, we moved to the notion of heterogeneous computing. We saw, we also went deeper into some of the definitions that were introduced in week 9, like command queue and device. And then we looked at what are the possible ways in which you can program multiple devices using OpenCL, different ways of putting in putting in contexts and command queues for devices, and then we also looked at how do you execute kernels concurrently. We looked at partitioning, we looked at device fission and things like this. And then finally we looked at concurrency and CUDA. So we looked at streams and we looked at synchronization. So we'll look at a detailed recap of some of these topics, and if you have any questions in anything else that's not covered today, please feel free to ask. You can either ask, since no one's attending the session right now, you can either ask when you watch the YouTube video. If you have a comment, you can leave it on the YouTube channel as well, or you could even ask on the discussion forum, right? Since we have only 2 more live sessions left, I would like to address all your questions within those 2 weeks. So make sure to ask if you have any doubts. Okay, with that, let's get started. Okay, so what is heterogeneous computing? So computing platforms with more than one kind of devices, processors or cores are called heterogeneous platforms. So let's pause here for a moment and tie this back to something we've learned in a previous lecture, right? This is something important to do as you kind of progress more and more into the course, right? Whenever you learn about a new concept, try and see if you've heard about it elsewhere, maybe in an earlier lecture, maybe even in a different subject. That will help kind of make your big picture more coherent, and it'll also, because questions that you get in the final exam or anywhere else may not be limited to one topic. They might be connecting 2 topics, right? For instance, a question may be asked combining something from week 9 and week 10, or maybe week 1 and week 10, right? So always try to make those connections. So for this one, the heterogeneous computing, if you remember in the earlier lectures, maybe lecture week 3 or week 4, we were studying the types of GPUs, right? So one of the devices we studied, I think, was in the embedded class of devices, the Jetson. So if you go and look at that device's architecture, right, you'll see very clearly this heterogeneous computing. So it has a CPU, it has a GPU, and it also has other custom accelerators for deep learning, right? One of them is called the DLA, there is another one called PVA, and so many more. So this is a perfect example of a heterogeneous computing platform, even in other machines which kind of look homogeneous to you. For instance, you might hear of a machine that has 8 CPU cores, right? And you might think this is just multiples of the same thing, but it might not be the case. For instance, sometimes you'll see this, you'll hear this phrase called big little architecture, where some processor cores are supposed to be big in the sense that they can handle more compute, and some more cores are little, right? In that they are meant for lightweight workloads. So this is an example of, again, heterogeneous computing, where there's heterogeneity in terms of your processor cores, right? And there is also, in this big little world, there is also a difference in the power consumptions. So this is, I think, something introduced by ARM. Feel free to look it up. So yeah, that's broadly defining heterogeneous computing. And heterogeneous computing typically utilizes this heterogeneity to gain performance or energy efficiency. So let's say I have two different types of processing elements, right? One is the GPU and another one is some custom hardware, let's say some kind of an ASIC, right? Now, it might be the case that for a given workload, the GPU is very fast. It gives you very good performance, but then it consumes a lot of energy. On the other hand, the ASIC might be quite slow compared to the GPU, but it takes very little energy, right? So, depending on what is your goal, you might choose either this or this for your computing. If energy is a constraint for you, then maybe you go with this. If performance is a constraint for you, maybe you go with the GPU. Or if you want something intermediate, this is interesting, right? If you want something intermediate, let's say you say, I can't afford for my workload to be as slow as running it on the ASIC, but I don't need it to be as fast as the GPU also. So what can I do? One thing you can do is try to split it across the GPU and the ASIC, so that you get somewhere midway in terms of both performance and energy efficiency. And this is not a hypothetical example that I'm giving you. There has been research done on this, right? So if you look up workload partitioning in heterogeneous compute, you'll see a lot of literature on this. So this is where heterogeneity becomes really interesting. You can gain benefits out of having non-uniform hardware. And concurrency, again, I think we saw the definition much earlier. So if you have an application, like I was just telling, right, where you have an application that's executing functions concurrently on multiple processors. And OpenCL is an ideal programming language for heterogeneous computing, as it supports programming across multiple computing devices. Again, this I think we've seen enough in week 9, where we said what are the kinds of devices and hardware vendors that OpenCL supports. We also looked at how different it is from CUDA, and we also saw the kinds of hardware that it supports, right? It's like CPU, GPU, FPGA, DSP, all sorts of things. So OpenCL is kind of made for heterogeneous computing in that sense. Then, so again, going a little more into heterogeneous computing, the idea is to use your available compute or processors or processing elements efficiently. So if I have 4 different kinds of processing elements and I'm using only one of them for my workload, then the other 3 are kind of idle, right? So this comes to this notion of hardware efficiency or utilization, where you're not utilizing your hardware well enough. So if you are able to, like I was saying, partition your workload or run multiple things in such a way that all of these are utilized, it might give you performance benefits as well, and you're utilizing all the hardware on the board, right? But what is the challenge in doing this? So firstly, like I said, here I was giving you this example. For a given type of workload, I said the GPU is much faster, the ASIC is much slower, right? First of all, you need to identify that which processing element is suitable for a particular kind of workload. Or if you break down that workload into multiple tasks, you need to identify which task to map to which device. And again, like we said earlier, this itself should not take a long time, right? If you're trying to do one of these optimizations, figuring this out, if it takes longer than actually running it, it kind of defeats the purpose. So this has to be lightweight. Then you also need to minimize overheads due to data transfers, synchronization, etc. So in a way, it makes it a lot more complicated than a single GPU or a homogeneous system, right? So these challenges need to be handled efficiently to get the advantage of heterogeneity, to get either performance or energy benefits out of heterogeneity, these challenges need to be handled properly. Yeah, this is just a pictorial example. Here you have two CPU cores that are from AMD and one GPU. You also have an NVIDIA GPU. So this is your computing platform. Now we've looked at definitions of context and command queues, so I won't go into that too much. So you have three devices here, device 1, 2, 3. So they're labeled a little, so this whole cluster is called device 1, where 1 is the subscript. Then you give superscripts to indicate the device number within that cluster, right? That doesn't matter. You can even call this 1, 2, 3, 4 for our discussion now. It doesn't matter. So what do? You have one command queue for each of these devices, and you create a platform. I think this was a question last week. You can create a platform out of multiple kinds of devices as long as they are from the same vendor, right? And that's what you see here. You're creating a platform out of 2 CPUs and 1 GPU, and all of them are from AMD, right? And yeah, other than that, I think it's straightforward. And platform 2 just has the NVIDIA GPU, which maps to one device, and that maps to one command queue. Right, so going more into detail into the command queues and devices. So one command queue can only be associated with one device. Now, going the other way around, what we've already discussed is single device being associated with a single command queue. This we already touched upon. Other than this, you can have a single device being associated with multiple command queues, and this can be in the same context. You could also have the same thing, which is single device associated with multiple command queues, but with different contexts and within the same platform. So these are two variants that you have for single device, multiple command queues. Then going on to different devices can also be associated with multiple command queues, either with the same context or with different contexts. Now, why do you do some of these things, right? We'll see a few examples. So, starting with single device, same context, multiple command queues. Why do you do this? So, why you do this is to get some kind of performance benefits, right? So, you overlap execution of different commands, or you overlap some compute and some communication. So, basically, let's say we have one single device, one single context, and you have two command queues, right? Now what I can do, this is in a way some sort of logical parallelism, right? I can queue in kernel 1 here, I can queue in kernel 2 here, and maybe I can even queue in, like this says, here there might be something computing, and here there might be something that has communication or data transfer, right? So even if one of them is blocked, the other one can still run, right? So the commands are executed independently. So that allows you to queue multiple independent commands without requiring synchronization, because at a software level you are separating these into two different command queues. So as long as these objects are not being shared, this is fine. Moving on, multiple command queues with the same context in single device example. Okay, so here's an example. So let's assume 3 independent tasks that need to execute on a device. Now what we do is we create 3 command queues with tasks enqueued in each of them. So now what you can do is you can kind of imagine this pipeline such that the device executes the kernel code while I/O is being performed. So this helps achieve better utilization because the device need not sit idle waiting for data. So yeah, I think we've seen enough of these pipeline diagrams. So this is probably very easy for you to imagine. If not, ask me next time, I'll explain it to you. But this is kind of the intuition behind why we do that. Moving to other different kinds. So this is multiple command queues with different contexts in a single device. So why would you create multiple contexts for the same device on the same application? Typically, we don't do this. It doesn't have any benefit. Sometimes, if an application uses OpenCL for certain operations and it also uses a third party library that then again calls OpenCL internally, then such a use case might be beneficial, right, for this case. So, if you have an application that uses OpenCL and that also uses some library that acts as a wrapper around OpenCL, then you can have two different contexts for both of these partitions, right? And it is still in the single device, but it makes sense to have different contexts in this case. Then finally moving on to the multiple device case, it's basically two execution models. Two or more devices work in a pipeline manner such that one device waits on the results of the other. The second one is a model that where both of them work concurrently, independent of each other, right? So here there is a dependency of sorts, right? So one device kind of waits for this one, but here it is kind of concurrent. You can imagine it like this, two parallel things, right, that get inputs from different places. So these are the two different models. Okay, so moving to the multiple devices case, multiple command queues with same context in different devices. So each device of course needs its own command queue, right? So here you cannot have a single command queue at all, has to be multiple command queues. And the typical way to work with multiple devices is creating a single context, because memory objects are globally visible to all devices within that context, and an event is only valid in a context where it's created. So a single context is the typical use case. You could also have multiple contexts, but we won't go into the details of that. So with this, we'll move to a slightly different topic, concurrent kernel execution. Again, we spoke briefly about what is concurrency, right? Basically, you have a set of tasks and they remain active and make progress at the same time. That's concurrency. I think in the earlier classes, I also had a slide on the difference between concurrency and parallelism, right? So if you have any questions around concurrency, the basic idea, again, ask me. Right. So as a programmer, what you need to do is identify the concurrency in the problem and then efficiently schedule it in the host program. So concurrent tasks can be different kernels from different independent applications, right? So if I want, these are different examples, right? So I might have task 1 and task 2 from two different applications, right? These are not at all related. They have nothing to do with each other. So they can be running concurrently. This is your case 1. Case 2 is different kernels without dependency between them, but from the same application. So if you think of an application in the form of a DAG, right, a dependency graph of sorts, then you could have something like this, something like this. So if now I cannot execute this one and this one concurrently because there is a dependency between 1 and 2, but I can execute 2 and 3 concurrently as long as their inputs are ready, right? There is no direct dependency between them in that sense, right? So it could be something like this, or you could take a single kernel and actually partition it, split the data of some sorts, right? That is also valid. That can also be concurrent execution. So yeah, this is about partitioning. So some kernels perform better either on CPU or GPU devices, but if you, like I was saying, right, the first example that I gave, if you pick a specific device for the kernel, the other available devices may remain idle. So partitioning is a technique where you split the data across multiple devices, right? So how do you do this? Now think of this, right? Again, we'll go back to that example. Let's say the GPU is 10 times faster than the ASIC or the custom accelerator that I was using in the previous example, right? Now, what happens if I blindly do, let's say I have 2 power, or let's take an easy number, right? Let's say I have 500 elements in my array. Now what happens if I naively split it up as 250 250? Instead of having one kernel process all the 500 elements, now I'm going to have two kernels. One is going to run on the GPU, one is going to run on this custom hardware, and kernel 1 will process first 250 elements and kernel 2 will process second 250 elements. The problem is the GPU is 10x faster, right? So if you give both of them the same amount of data or the same number of elements, the GPU will finish in 1/10 of the time and sit idle, whereas the ASIC is much slower, so it's going to take a lot more time. So you have to partition them cleverly, right? So here, for instance, I have to give the GPU 10x more data than the ASIC so that it kind of finishes at the same time. So one simple partition I can kind of come up with right now is 450 and 50, right? Now this way what happens, you're going to sort of finish almost at the same time, because the ASIC is much slower, so it's going to take a lot more time than the GPU. But do you get a benefit out of this? This is also something you need to think. Is the benefit only that I'm using all the hardware on the system, or do I actually get some benefit out of it? So here in this case, there is a small benefit, right? Earlier the GPU used to take some amount of time for 500 elements. Now 450 elements is all that it's going to execute on. So it might take a slightly lesser time, right? So that way there might be some performance benefit that you have. But this is also something you need to ask yourself as a programmer. How can I partition so that I can get the best of this heterogeneity while also getting some benefits out of it, right? So this is what this talks about. Launch the same kernel with partitioned data across multiple OpenCL devices. They can run concurrently on different devices, reducing the total execution time. This is what we just saw. Right, here's a pictorial example. So this is 100% to CPU, GPU, and instead it is some X% to CPU, Y% to GPU. Again, like I said, you can see the larger fraction being given to the GPU and the smaller fraction to the CPU. And now you can see the time. The CPU takes this much, the GPU takes this much. Your overall time kind of comes down to the slightly less than what the GPU used to take, right? So not only are you using both the CPU and the GPU, so there's no hardware idle, you're also getting some benefits in terms of what used to be the fastest earlier, which is your GPU time, right? So that's pretty much it. So next we will move to concurrency and CUDA. So this is kind of going back to CUDA. Remember that the earlier ones were all in terms of OpenCL strictly. This one is kind of going back to CUDA. So remember that this is a CUDA concept, right? Streams is a CUDA concept. So applications must execute functions concurrently, so that, again, this is the same thing we've been seeing. So CUDA applications manage concurrency by executing asynchronous commands in streams, sequences of commands that execute in order. Different streams may execute their commands concurrently or out of order with respect to each other, right? So again, this stream is a logical notion that you have, kind of like your command queue in OpenCL. So you can you can have logically multiple streams, and then you can kind of execute commands across them so that you get concurrency, and so that you get some performance benefits out of doing that. So the programming mechanism for that is called CUDA streams. So a stream refers to a sequence of asynchronous CUDA operations that execute on a device in the order issued by the host code. These can include host device data transfer, kernel launches, and most other commands that are issued by the host but handled by the device. Execution of an operation in a stream is always asynchronous with respect to the host, right? It's again like the command queue. You queue it in a certain order into the command queue, but then afterwards is when it is executed, right? So you don't have control over that. It's always asynchronous. The queuing will return, like the kernel launch. It returns as soon as it is put into that queue or it's put into that stream. But later is when the kernel is actually executed, right? So it is a programmer's responsibility to use the APIs to ensure that an asynchronous operation has completed before using the result. Simple example, right? Let's say I copy data and I use an asynchronous copy command, right? And now I launch a kernel that kind of uses this data that is supposed to be copied. Now, in the CPU world, what do you think? Unless a call is explicitly asynchronous, you think, okay, the control has returned from this command. That means that this command has finished executing. Therefore, I can execute the next command and this data will be available. But remember, in the GPU side of things, when we use asynchronous operations like an asynchronous copy, that might not be the case. So now if you launch the kernel, what will happen? That's a question I think that was also asked in the discussion forum. So we will discuss it in a few minutes. But remember that as a programmer, you have to be aware of these things and use the asynchrony appropriately. Right. So all CUDA operations, whether it's some compute in the form of kernels or whether it's data transfers, either explicitly or implicitly run in a stream. So there are two types of streams: implicitly declared stream, which is called the null stream. So if you as a programmer don't declare a stream, right? We saw many kernel launch commands that didn't have this fourth stream parameter. They just had the grid and the thread dimensions. So you could have something like that. Then it becomes an implicitly declared stream. All your commands go to the same stream. That's called a null stream. And explicitly, so it's kind of like a default stream. Explicitly declared stream is when you give a stream parameter to a kernel command, like we saw in the examples in class. So then it goes to that particular stream, and this is not a default stream, and it's not a null stream, right? Again, yeah, like I said, the null stream is the default stream that all kernel launches and data transfers use if you don't explicitly specify a stream. All examples discussed previously use the null or the default stream. Now, to exploit concurrency, what are the various things we can do, right? One is asynchronous stream-based kernel launches and data transfers enable the following types of constraint concurrency. So one is overlapping the host computation and device computation. So these are two different things, right? So they can happen concurrently. Similarly, you can have host computation going on and host device data transfer going on. And again, vice versa, you can have host device data transfer going on with device computation. Finally, concurrent device computation, and this one will probably need to have a little more, it might need to have kernels that are kind of not dependent on each other and things like that. But typically, first optimization is to overlap data transfer and computation, right? I think we even saw those, yeah, this diagram is what I was talking. So if you do something serially, it looks like this, right? It's a host to device copy, then it's a kernel execution, and then it's a copy back, device to host. Now if I do this concurrently, so it's basically the same pipeline diagram that we saw, I think, in week 0 or week 1. So there is a host to device copy, then kernel 1 starts executing. Now the copy is kind of the hardware that does the copy, right? Typically the PCIe bus and things that are involved in that are free. So you can typically do a host to device while the kernel 1 is going on, right? So that's what is shown here. Then here comes the tricky part. So you have both a D2H and a H2D going on. So this is what it says. Data transfer operations are not executed concurrently even though they are issued in separate streams. This is because there's a contention caused by a shared resource, the PCIe bus. Devices with a duplex PCI bus can overlap two data transfers, but they must be in different streams and in different directions. So these two are in different directions and in different streams, right? So if you have a duplex PCI bus, this will happen concurrently. But if not, then even though they are scheduled in different streams, because of hardware contention, they will not happen concurrently. Always. So one is the logical level at which we draw all of these things and we say, okay, there are streams and they'll happen in parallel. But always keep the hardware in mind, right? Think about what hardware does this use? Is that free? Can I really do this in parallel, right? That's important to be aware of, because sometimes things that we think will happen in parallel or concurrently will not actually happen that way. Right, so we'll pause here for a minute and move on to the discussion forum questions. Use this minute to look through all the contents of week 10, and if you have any questions, please ask them offline, of course, because yeah. Okay, let's move on to the discussion forum questions. Yeah, so this was a question I was referring to. So this is about the kernel launch with an async data copy. So the person says, in asynchronous data copy, the operation being done here, there are two host to device data transfers happening on the same stream in one iterations. We can't overlap these copy operations, so one will be followed by the other. But can the kernel launch be done at the same time when data copy operation is being done on the same stream asynchronously? So data is still not ready at the device side, but we are launching the kernel on that stream in this iteration. Can you please explain how kernel will execute in this case where data is still not copied completely by async copy? So this is a simple question, right? So this is, let's say this is one stream S1 and this is a copy of data, and this is done asynchronously, meaning it will enqueue that copy command and immediately return to the host, but the copy might not actually be finished yet. and right after that we are doing a kernel launch. So the person says, how will the kernel execute, because the data is not ready? It's just that the copy command has returned because it's asynchronous. So let's see the answer to that. In CUDA, kernel launches are asynchronous and can be overlapped with data transfers on the same stream. However, when launching a kernel on a stream that is still copying data asynchronously, the kernel will wait for the data transfer to complete before executing. So this is a simple sanity check, right? So if the kernel doesn't have the data that it needs to execute, it is going to wait for that data to become available, right? When a kernel is launched on a stream, the CUDA runtime checks whether all the data required by the kernel is available on the device. If data is not available, the kernel launch is added to the stream's command queue, and the CUDA runtime proceeds to execute the next command in the queue, which might be a data transfer operation, right? So whenever you try to launch a kernel, it's a sanity check, right? The runtime will check if the data is available or not. If it's not available, then you take this kernel launch and add it back to the command queue, and then the next command will be executed. Now, if a kernel launch is added to the command queue before the data transfer completes, then the kernel will block and won't execute till the data is available. So this can lead to inefficient use of resources because the device will be idle waiting for the data transfer to complete. So this is not a good idea, right? Because the kernel is actually not doing anything, but it's also blocking. So to avoid this, what is recommended is you overlap the kernel execution with data transfers by launching the kernel after the data transfer is complete, or by launching multiple kernels on different streams, so that at least some other kernel from a different stream can execute on the GPU. Because ultimately it's the hardware that's idle, right? It doesn't have to be another kernel from the same stream. It can be a kernel from the different stream. So that would take advantage of the GPU's parallel processing capabilities. This will help maximize utilization of the GPU's resources and improve performance. So to summarize this whole discussion, when you launch a kernel on a stream that is still copying data asynchronously, the kernel will wait for the data transfer to complete before executing. So to avoid this, generally we overlap the kernel execution with data transfers by launching the kernel after the data transfer is complete, or by launching multiple kernels on different streams. These are two options that you have. If you don't do either of them, then if you use an async copy, the kernel might block because the data is not yet available, and that will lead to the GPU being idle. So you don't want that to happen. Hope this is clear. Let's move on to the next question. Command for GPU architecture viewing. Is there any similar command like lstopo or hwloc-ls for CPU? These are basically for CPU architecture's pictorial view for GPU architecture viewing. Also for NVIDIA based GPUs, NVIDIA SMI gives some ideas but not architectural views. So the answer is there are several similar commands that can be used to obtain a pictorial view of the GPU architecture depending on the hardware and the OS. So again, this first one, NVIDIA SMI, is for NVIDIA GPUs. ROCm is for AMD GPUs. CLI info is for OpenCL platforms, and then additionally CUDA toolkit has several tools that allow you to get various information about the GPU. So let's go through these in detail. NVIDIA SMI, a command line utility provided by NVIDIA that displays information about NVIDIA GPUs installed on a system, including GPU architecture, memory usage, and performance metrics. It also provides a GPU topology view that shows the interconnectivity between multiple GPUs. Then coming to ROCm, this is a command line utility provided by the Radeon Open Compute platform that displays information about the AMD GPUs installed in a system, again including architecture, memory usage, and performance metrics. Again, it also has a topology view. CLI info, similarly the exact same thing for OpenCL platforms and devices. Similarly, you can see a hierarchical view of the OpenCL devices, their relationships and interconnectivity. Finally, CUDA toolkit is not really a tool, it is a set of tools, right? It has multiple things, and some of them can be used to obtain this pictorial view. And you have tools, profiling tools like NVProf, NVVP. This is a visual profiler. NVProf is again a profiling utility that gives you detailed performance analysis. So all of these commands can help you get some good insights into architecture as well as performance. I'm hoping that is clear. Let's look at the next question. So I think I've picked up all questions that were asked up to yesterday. There might have been one question today that I haven't picked up, but I don't think that's been answered yet. So we'll look at that in the next week. Okay. So the next question is about DRAM. DRAM is divided into two broad parts that do not communicate with each other. One part, local memory, is exclusive for thread computation, which is private to each thread, while the other part is the global memory accessible to each thread, making communication between threads possible within a given SM. Have I understood this correctly? So let's see this. The description you provided is not entirely accurate for all GPU architectures, but it might apply to some. In general, GPUs have a hierarchical memory organization that includes several levels of memory hierarchy with varying levels of accessibility and latency. At the highest level, so remember this memory hierarchy triangle or pyramid that we saw, right? We saw this both for your typical CPUs and also later, I think, for the GPUs. So we spoke about how some things are really fast but very small, and what portions of a GPU can access it and all those things, right? So this is just a recap of that. At the highest level of the memory hierarchy is the global memory, which is accessible to all threads in a kernel and is typically used for storing data shared among threads. Global memory is lower than the other levels of the memory hierarchy, but has a large capacity and is optimized for high bandwidth data transfers. Below this is the shared memory, also called local memory in some architectures, which is a small fast memory that is shared among threads in a block of threads. The shared memory is used to reduce memory latency and improve memory access performance, and it is used for storing data that is shared among threads within a block. Finally, each thread has its own private memory called the register file, which is used for storing local variables and intermediate results that are specific to each thread. The private memory is the fastest memory in the memory hierarchy, but it has the smallest capacity. It's important to note that the shared and private memory are physically part of the same memory space as the global memory and communicate with each other through the same memory bus. Therefore, they are not completely separate and independent, and the distinction between them is more of a programming model than a physical separation. So, in summary, the global memory is accessible to all threads and is used for storing data that is shared among threads, while shared memory is shared among threads in a block, used to reduce latency and improve memory access performance. Each thread also has its own private memory for storing local variables and intermediate results specific to a thread, right? So the main part of the answer, I think the distinctions between global, local and shared memory you already know. This is just a recap, so we won't go through that a lot. But the important thing to take away from this is understand what is a logical separation versus a physical separation, right? When we talk about different parts of memory, are we talking about different things physically, or are we talking about different things logically, right? So even in the CPU case, for instance, or in the case of an integrated GPU, we might say there is no such thing as a GPU DRAM there, right? There's no dedicated GPU memory that is there. So the GPU uses the same RAM that is available to the CPU. But logically, you might still hear this term of GPU memory and CPU memory, right? So logically, they are two separate things, but physically, it is the same DRAM chip, right? It's the same memory DIMM that you put in. So that's something to keep in mind. Whenever you hear these things, try and observe if they are physically two different things or if they're just logically separate. That's the main takeaway from this answer. Next, from a computational point of view, for offloading workloads to run parallelly, how are Apple's GPU and Neural Engine recently launched Intel's Arc GPUs and Cerebra's wafer scale engine different from traditional GPUs like those offered from NVIDIA, ARM, or Qualcomm? And from programmers' point of view, which offers friendly architecture to code for parallel execution of workloads? I'm asking because CUDA is a bit scary and a nightmare even to install for a novice like me who is trying to understand its working. Haven't tried OpenCL yet. This is an interesting question, right? So there's a lot of hardware coming in today. If you've noticed, like this person says, there is Apple launching some things, there are Intel's GPUs, and then there's wafer scale compute. Then there are hundreds of other things that are not mentioned in this, right? For instance, Google's TPUs, and then Intel has this line of Movite's products, which they call, I think, VPUs. So it's really XPU at this point. There's hundreds of different hardware, right? So as a programmer, what you care about is which of these offer programmer friendly architecture to code for, right? How much of the architecture do you need to be aware of to write a program that performs efficiently? And how is the environment? How easy is it to install? How easy is it to get support and debugging and things like that, right? So that's the main point to this question, and this is a question beyond this discussion forum that you'll have to take a call at in every part of your career, right, in tech, because there are a wide variety of libraries and toolkits at this point in time, and as a programmer you have to kind of evaluate them for both performance and how easy it is to use before you make a choice. So let's see what the answer says. So the answer says all of these types are specialized processors designed for specific types of workloads. Here are some key differences between them. Apple's GPU and Neural Engine, these are integrated into their mobile and desktop devices and are optimized for running machine learning and other AI workloads. Neural Engine in particular is designed for running neural network models and performs computations such as matrix multiplications, convolutions, and activations much faster than a traditional CPU or GPU. These are tightly integrated with Apple software and hardware, providing a seamless user experience and high performance for specific workloads. Again, this is hardware that is intended to accelerate mostly machine learning and AI workloads, right? So typical operations that are used in those are matrix multiplications, convolutions, and some activations, right? So these GPUs or neural engines will be much more efficient at those than your GPU or CPU. Basically, it's custom hardware built for that particular thing. Then coming to Intel's Arc GPUs, these are designed for data center workloads and built using a new architecture that allows for greater customization and scalability. Unlike traditional hardware, which uses fixed function for specific tasks, Arc GPUs use a more modular approach that allows developers to customize the hardware to fit their specific workload requirements. This again allows for better performance and efficiency. So this might be a bit abstract for you, but we can't go into the details because you've not studied this architecture, right? So even if we tell you an exact sentence here, you won't be able to make sense of that without going into the architecture. But try to observe what these things are designed for, right? Like here we said it is optimized for machine learning and other AI, and it said this is in the mobile segment. Whereas if you notice here, it says it's for the data center segment. So that's a different use case, and depending on that, there might be certain hardware and architecture choices that are made, right? So this is about Arc, and then there is Cerebras, which is a massively parallel processing system that's again designed for deep learning. It is built using a unique design that combines multiple processing units on a single chip. resulting in a high performance and power efficient system. Unlike traditional GPUs, which typically have hundreds or thousands of processing units, this has over 1.2 million processing units, allowing for extremely high levels of parallelism. Again, you can see that this is a very custom type of hardware. It is designed specifically for deep learning workloads, and again, a lot of this hardware that you'll see is being used for deep learning, and that's why I think week 11 and week 12 also deals with deep learning workloads, and you'll learn a little bit about this if you've not already done so, right? And this is parallelism at a different scale even compared to a GPU, right? It has millions of processing units. Again, since it's for deep learning workloads, it's catering to that particular kind of workload and making certain hardware choices that again come from the workload. So in general, these specialized processors are designed to provide high performance and efficiency for specific types of workloads, whereas traditional GPUs are more general purpose and can be optimized for a wide range of workloads. These can offer significant advantages for specific types of workloads, but they might not be as versatile as traditional GPUs. So it's a trade off, right? You pay a certain price for getting that extreme performance for what you want. They might not be able to deal with other things as well, right? Now, coming to the second part of this question. So, the first part of this question was how are these different, right? We touched upon a little bit of that here. Second part was which of these are programmer friendly. So, this again, there is no one size fits all answer, right? So, what we say is the architecture that offers the most programmer friendly approach depends on the specific use case and the language being used. In general, architectures that provide high-level abstractions and libraries for parallel programming can make it easier for programmers to write parallel code. And again, we talk about CUDA, OpenCL, MPI and OpenMP, which I think we went through in the last lecture. So I'll skip all of that here. I think we've covered all of these. And it summarizes by saying the architectures and frameworks provide different levels of abstraction and support for parallel programming. So the choice of which one to use depends on the specific needs of the application and the preferences of the programmer. However, installation and initial setup also have some one-time overhead. So again, this is not a very precise answer, right? We say that it depends on the specific use case, the language, how familiar the programmer is with some of those, and that's valid enough. For instance, if you've already used CUDA and you're using CUDA from say 4 or 5 years, you might have a bias saying, I know how to install it, I know the tools, I know the environment, therefore I will go with this, right? Because it's a world that you already know. Or it might be for this particular use case that you're looking for, OpenCL might be the best one, right? So this is not something that we can answer in a very generalizable fashion. There is no such answer, right? It has to be decided on a case by case basis. And you as a programmer will be doing that by looking at the hardware, looking at the libraries, figuring out what is the effort in this installation and setting up, what are the benefits that you gain by using a particular library. So even now when you're studying these different paradigms and different libraries, ask yourself how difficult is it to write CUDA versus OpenCL. And if you said CUDA is easier, then does OpenCL give you certain additional benefits for the extra complexity? When would you use OpenCL? When would you use CUDA, right? So thinking about these things will give you more perspective on questions like this. Okay, so with that, we are at an end. We come to an end of the discussion forum questions. We finished recap and discussion forum, so I think we just have the problems left. And since we are almost at 8:05, this is a good time to take a break. So I think it's almost 8:05 by my clock, so we'll resume at 8:10. Okay, let's resume. First question. Suppose an application uses OpenCL for certain operations and also uses some third party library that also happens to use OpenCL internally to accelerate some algorithms on a single OpenCL supported GPU. What will be the preferred choice for context and command queues in such a scenario? Single command queue with single context in a single device, single command queue with different contexts in a single device, multiple command queues with different contexts in a single device, multiple command queues with the same context in a single device. So I'll pause here for 30 seconds to a minute so that you can have time to solve it even while watching a video. Okay, let's look at the answer. It is multiple command queues with different contexts in a single device. Why single device? It's just one single OpenCL supported GPU, and we saw this that you could use multiple command queues with the same context and multiple command queues with different contexts. And we said that the only case where it makes sense to have multiple contexts with a single device is something like this, where you have a library that uses OpenCL internally, right? So go back and look at the slides if you want more clarity on this. If you still don't understand, again ask. Let's move on. What is the advantage of implementing multiple command queues within the same context in a single device for an OpenCL code? Helps in faster data processing by improving synchronization, reduces kernel launch overhead by having multiple command queues, pipeline can be formed by better utilization by not having the device sit idle waiting for data, improves data sharing across multiple command queues in the same context, thus improving performance. Again, take a minute. Okay, let's look at this. Again, this is also easier. Pipeline can be formed for better utilization by not having the device sit idle for waiting for data. So basically you have one GPU, right? if I have multiple command queues, then in case one of them has to do a data transfer or something like that, my GPU won't have to be idle. It can execute kernels from all these other things, right? So that's the pipeline that this talks about. The other answers are not valid. I think it's straightforward and you can figure that out. We will move to the next question. Consider the reduction kernel to find the maximum of a given data set, and the data set size is this 1048576. The kernel looks like this: shared int sdata of 2048, then you have your TID, you have your I calculated this way, and you fetch sdata of you populate sdata of TID with g I data of I plus g I data I plus block dimension dot x. Then within the for loop, if TID is less than s, sdata of TID is max of the TID and TID plus s. And if TID equal to 0, g of O data of block ID of x equal to s data of 0. Now, to this kernel, if you apply thread coarsening with coarsening factor 4, and given that the maximum size of a work group that can be launched is 1024 work items, and the kernel invocation command is this clnqnd range kernel with commands max coarsen 1 null, global work size, local work size 0 null null. So what is the content of the arrays? Global work size and local work size. You have 4 options. So this requires you to connect two concepts together. So we already did problems where we figured out global work size and local work size given a kernel. We also did problems for thread coarsening. Now here, with thread coarsening, you need to find out the local and global work size. So I'll give you maybe 3 minutes for this question. Take your time and solve it, and then we look through the solution. Okay, let's look at the answer. The answer is C, 26214411. Local work size is 102411, right? Now let's again try to reason through this in two steps. One without the thread coarsening. So without the thread coarsening, I think it is straightforward, right? So you need the size of your array is 1048576. So totally your global work size needs to be that, and since it's all 1D, you could have a 1D global work size and local work size, and your local work size can be set to the maximum, which is 1024, right? Now let's consider thread coarsening. So if you have thread coarsening with a coarsening factor of 4, meaning that now you're going to have 4 times lesser threads, right? What is the global work size? So you take the number of elements, which that huge number that we saw, which is actually 2 power 20, divided by the coarsening factor, which is 2 power 2. So what you get is 2 power 18, and this is that 2 power 18. So you just take that and divide it by 4, right? Because you have that many fewer threads now, and your local work size remains the same. So this is the answer for this. Hopefully it's clear. Let's move on. The execution of an operation in a CUDA stream is always synchronous with respect to the host. True or false? I'll give you 30 seconds for this. Should be fairly straightforward. Okay, let's look at the answer. It is false, right? You could have asynchronous operations that execute in a CUDA stream. So the host will just enqueue that operation into the stream and then proceed, right? But the operation itself might happen later. For instance, a copy operation which we discussed earlier. So this need not be true. Next, device fission can be helpful in the following cases. Dividing CPU-like devices into smaller subdevices to build a portable and powerful threading application based on data parallelism, to merge multiple devices to increase parallelism. So you have multiple options which are combinations of 1, 2 and 3. See if you can figure this out. Again, we'll take maybe a minute and then look at the answer. Okay, let's look at the answer. It is option B, 1 and 2. So fission can be about dividing CPU-like devices into smaller devices and to build a portable and powerful threading application based on data parallelism. 3 is basically the opposite of 1, right? It talks about merging multiple devices to increase parallelism. So fission and fusion are the terms that you might already be familiar with. So looking at fission, you should be able to figure out whether it's 1 or 3. And 2 is also one of the benefits that you have with this kind of division, right? So based on data parallelism, you can come up with a kind of flexible threading application. So 1 and 2 are suitable, and that makes the answer option B. Moving on. Okay, so this question I think was similar to something in your assignment, and the same data will hold for 2 or 3 questions. So pay attention to this. The given DAG with 3 kernels, basically K1, K2 and K3, the edge denotes that the output of the parent node is the input of the child node. This edge, right? Here, 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 here. Kernels are executing in an out of order fashion. Assume that the target hardware has one AMD CPU and one AMD GPU. All inputs and output buffers are of the same size and dimension. Q CPU and Q GPU are the command queues for CPU and GPU. Data size is the variable for data size. DA, DC, DE, HA, HC, HE are the CL buffers and memory at host side respectively. The global work size and local work size are given by this global WS, local WS. E1 to E6 are the CL events. I'll come back to the slide and pause here if you need some information. So these are the commands, right? And you're supposed to fill in the blanks here. So the first two are NQ write buffers, which basically take care of the copy from the host to the device. And then you are NQing the kernels K1, K2 and K3. And then finally you have the read buffer to read the data back into the host, right? And some things are already populated here, and the last, basically the event, is also populated. There are two blanks in each of these statements, and the questions that follow will ask you about what are these blanks, right? So I'll pause here for 30 seconds and then maybe I'll go to the question, come back, pause at both of these slides for 30 seconds. So the question 6 asks you about the first 4 blanks, 1, 2, 3, 4, and you have different options, which are 0, 1, null and some events, right? So this is your options. Before I come back to the screen, so I'll give you 3 minutes to solve this. I'll pause here for 30 seconds, then move to the next slide and pause there for 30 seconds. Finally hold at the option slide. Since this is a long question, I know you need to refer back. Okay, let's move to the next slide. And finally the option slide. So now you can take 2 more minutes. Okay, I hope that's enough time. Let's look at the answer now. So option A, which says the first blank is 0, the second blank is null. Similarly 0, null, right? So for an NQ write buffer, first of all, what are these two blanks, right? So the event was populated, if you remember. The events were E1 and E2 for these two write buffers. The other two were the blanks. So those other two indicate the event wait list and the number of events in the wait list. Now think about this. This is the first write buffer happening, right? So how many events do you have in the wait list? Nothing really, right? This is the first thing that's happening. And therefore your pointer to an event wait list is also null. There is nothing actually happening. So it's your option A. Now let's move on to, I hope that was clear. The other questions will be very similar and easy to answer if you followed this. So the next question asks you about blanks 5, 6, 7, 8. So let's look at those blanks once, right? 5, 6, 7, 8 are again the second last blanks. E3 and E4 are populated for the NQ kernel commands of K1 and K2. Now I guess you're familiar with this diagram and this, so I'll directly stop at the question. So again, you can take 2 minutes to solve this and then we look at the answer. Okay, I hope my video is still up. I'm sorry for that. I had a power outage here. We'll wait 1 more minute and then look at the answer. Okay, let's take a look at the answer. Here it's option D, which has one event in the wait list for both, and the event wait list is E1 in this case and E2 in this case. Again, it should be very simple. So let's again look at this, right? This is the kernel 1. So kernel 1 has to wait for this write buffer to complete, right, to have the data for its execution. So that write buffer was done by this very first statement here, and the event is E1. So there will be one event in its wait list and that event is E1, right? Similarly, the second kernel, which is K2, will wait for again one event, and that is the write buffer event with the second data that is needed. Okay, I am sorry again, I seem to be having a power issue. Give me a few seconds while my monitor stabilizes. Okay, hope that's still visible to you guys. Yeah, so the second kernel is waiting for this write buffer to go through, right? And that is given by E2. So again, it has one element that it's waiting on, and that is E2. So this is option 4. And I think you guys can figure out why none of the other options work here. We'll move to the next question. So question 8 asks you about 9, 10, 11 and 12. So let's take a look at those blanks. So 9, 10, 11 and 12 are 9 and 10 are for the third kernel NQ command. Again the second but last blanks. And then 11 and 12 are for the read buffer, the last command basically. So now you can, again I'll give you 2 minutes to solve this. Question 8, oops, sorry about that. You can take 2 minutes and solve this, and then we'll discuss the answer. Okay, let's look at this one too. So this is option C. So both of them, this one has two events in the wait list, and the events, the pointer to the events are E3 and E4. It's very obvious why that is, right? So we are talking about kernel 3, which has to wait for E3 and E4, which is basically kernel 1 and 2 finishing execution. So that has two events, and the two events are E3 and E4, whereas the last statement, which is the read buffer, has only one that it has to wait for, and that is E5. E5 is actually the event associated with K3 finishing execution. So before you read this, you copy this back to the host, this has to finish execution. That's all it is. I think it's very easy to understand. So with this, we come to the end of that set of questions. Now, the ninth question says, consider the same DAG as in question 1, but the kernels are executed in an in-order fashion. Assume the target hardware has one AMD GPU. All inputs and output buffers are of the same size and dimension. What will be the efficient method of synchronization? Command queue barrier for each command, CL flush at the end of all commands, CL finish at the end of all commands, waiting on an event associated with each command. Again, we can take maybe a minute to solve this. Okay, we can look at the answer. It is CL finish at the end of all commands. Again, I think this is a mixture of week 9 and week 10. So let's have a quick recap. So CL flush means that all queued commands in the command queue are issued to the device associated with this command queue. So it just guarantees that all the queued commands will be submitted to the appropriate device, but there is no guarantee that they will be complete after CL flush returns. CL finish, on the other hand, means that all previously queued OpenCL commands are issued and the function blocks until all previously queued commands have completed. It does not return until all previously queued commands have been processed and completed. This is the key difference here. Command queue barrier ensures that all previously queued commands have finished execution and updating memory objects before subsequently enqueued commands begin execution. This can be used to synchronize between commands in a single command queue, right? So these are the different things here. So coming back to our question, so for this DAG, CL finish would be more appropriate, right? Because if you do a CL flush, then you don't really ensure that the commands have actually finished execution. They are just issued to the device, right? Whereas CL finish means that it will return only after everything has finished execution, right? It's a blocking call. So this would be more appropriate here, because yeah, this should be enough. If you have some confusion about these, again feel free to ask. So coming to the last question of the day, consider an incomplete CUDA code using streams which processes a 2D matrix of dimensions W cross W using a 1D kernel. The matrix is stored in row major format. The 1D kernel processes the array in the following way. For the first row, the kernel processes W elements, for the second W by 2, for the third W by 4, and so on. Fill in the blanks. So this is what it looks like. So first you have a for loop which does the mem copies. Then you have a for loop which takes care of launching the kernels into different streams. And then finally you have the copy back again. All these loops are called once per stream, right? You have two blanks. One is for the offset, one is for the element. Now the question says, the values of ILM and I offset are the same for all the cases. Select the correct option from below. So I'll pause here for a few seconds and then go back to the question so that you have an idea. Okay, so I'll go back first to this, wait here for 30 seconds and then wait on the next part for 30 seconds. Okay, we will move to the next part. Okay, we'll now pause at the options, maybe for a minute. Okay, I hope that's enough time. Let's look at the answer then. The answer is option A, which is offset as I star W, and I element is W divided by 1 left shifted by I, right? So now let's take a look. So what are the two things? So first of all, we don't know the code of this kernel, right? We are given an incomplete CUDA code as the question says. But you need to tell the kernel, regardless of how the kernel is implemented, you need to tell the kernel two things, right? How many elements it needs to process in that iteration, and from where does that start, right? If not, you will not be able to execute it no matter what your implementation is. So first of all, we are told that the matrix is in the row major format, right? So you can look up row major and column major. It's just how a 2D matrix is stored in physical memory, right? So now we are also told that this kernel processes the array in this way. The first row, so the matrix is actually W cross W, which means that all rows are W elements wide. But for the first row, you process all W elements. For the second one, it's only W by 2. And then for the third one, it's W by 4 and so on, right? And this is done in iterations, right? These are launched to different streams through different kernel calls, and we are told that this offset and element value remains the same, but you need to figure out what that is. So how does this option make sense in terms of this question is, if you take I star W, right? So that gives you kind of which row this particular kernel should process. Let's say I is 2, then you do 2 star W. So you get this starting point from which the kernel has to process elements. Then the second element that the kernel needs is how many elements it has to process. So that is W by 4, right? How do you specify that? That is specified using I element. So it's actually W divided by 1 left shifted by I. So let's say I is 2. This becomes what? 4, right? So then it becomes W by 4. So you are telling the kernel that it needs to process W by 4, which is in agreement with what the question says. And you similarly, you can try and work this out for multiple things. This will not work because the offset itself is wrong. These three, the offset is right, but look at the element, right? If every element if every call of the kernel were to process the same number of elements, then that doesn't match what the question says. So this is also wrong. Then this is a slightly different variation of this, which I think you can work out and figure out how they're different, but you will find that option A is the correct one for this question. Okay, with that, I think we are at an end for the questions. So again, since there's no one attending live today, I'll repeat, in case you have questions not only from week 10 but from anywhere from week 1 to week 10 so far, please ask in the live sessions 11 and 12. We have 2 more left, so those are your last chances to get it clarified live, right? And so feel free to ask questions, whatever it is, whether it's from assignments, whether it's from course material, or whatever it is, feel free to ask. So I think I will wrap up with that. I'll stay around for a minute more in case someone joins and has doubts. But if not, see you all again in the week 11 live session, and hope to see some of you attend live. Thank you.